Today, modern commercial airplanes use jet engines with extreme power capacity. Some airplanes even have 4 of these gigantic engines. But how do these engines start and produce enough power to propel airplanes like the Boeing 747 weighing 183,500 kilograms? Before an airplane takes off, its engines need to be started and running to generate enough propulsion power to take off. To begin with, the pilot initiates the startup sequence in the cockpit by shifting the mode selector from normal to the start position. At the same time, the engine's master switch is switched on. This command prompts the activation of electrical power from a robust onboard battery. This electrical power drives an electric motor connected to a shaft on what's called the Auxiliary Power Unit, APU. Situated at the aircraft's rear, the APU is a compact turbine engine known for its distinctive high-pitched noise when the plane is parked. Its primary role is crucial. It provides ample volumes of slightly compressed air necessary to start the main engines. Next, the focus shifts to starting each main engine individually. The APU plays a key role in this phase by delivering the required air through an air turbine starter. Positioned beneath each main engine, this starter features turbine blades that spin as air passes over them, generating rotational energy. This energy is then transmitted through a series of gears to the high-pressure shaft of the respective main engine. Consequently, the compressor blades inside the engine begin drawing in air, compressing it in readiness for combustion. Here's a reminder to please like and share the video and subscribe to our channel to watch more educational videos on mechanisms, how things really work and what they are, explained in the simplest way possible. Let's continue now. As the engine takes in air through its intake system, the large fan at the engine's front starts to rotate. With these critical components now operational, the air turbine starter continues supplying energy until the engine reaches around 20% of its maximum revolutions per minute. This rotational speed is adequate to achieve significant air compression within the engine, facilitating the injection of fuel. The fuel is ignited using spark plugs similar to those found in household gas stoves. These spark plugs are important in initiating the combustion process within the engine by generating sparks that ignite the fuel-air mixture, resulting in controlled explosions. The energy released from these controlled explosions further accelerates the engine speed, typically reaching between 50% to 60% of its maximum capacity. At this stage, the air pressure generated by the compressor becomes so intense that it ignites the fuel independently of the spark plugs, indicating that the engine has become self-sustaining. Once the engine achieves this self-sustaining state, the aircraft systems stabilize, ensuring all engine parameters are within safe operational limits. This meticulous startup process is then repeated for each additional engine, ensuring consistency and reliability across all engines. Once the engine is running smoothly on its own, the next step is to disconnect the air turbine starter from the engine. This is done using a mechanical device called a centrifugal clutch, which is quite clever in how it works. This clutch has a central gear connected to the air turbine starter, surrounded by an outer gear linked directly to the engine. Inside this clutch are spring-loaded teeth. When the aircraft is at rest, these teeth engage fully due to the spring force, causing both gears to turn together. However, as the engine speed picks up, the centrifugal force acting on the teeth starts to oppose the spring force. To visualize, think of spinning a jug filled with water. The faster you spin it, the more the water moves to the outer edges due to centrifugal force. Similarly, when the engine reaches a critical speed, the centrifugal force overcomes the spring force, causing the pals to retract completely. This action effectively disconnects the air turbine starter from the engine, allowing the air turbine starter to stop automatically. Once the first engine is up and running smoothly, the process repeats for the second engine. The steps are almost identical, except instead of using the APU to supply air to the turbine starter, the air from the first engine is used. This ensures that each engine starts independently while following the same reliable sequence. Have you ever seen an airplane's engine being started? Isn't it fascinating that a single airplane engine can push away the cars parked before it? In the comment section right below, share your thoughts on what happens if any of the 2 or 4 engines of an airplane fails. Do you want to watch more videos like this one, where we explain complex processes and functions in the simplest and most logical ways? If so, subscribe to our channel and press the bell icon next to it. We bring videos on machines, mechanisms, and how complex things work. Thanks for watching, and until the next video, stay tuned.